So today we are revisiting trees in the sense that we are talking about binary search tree today, right? So if you remember binary search, anybody remember anything special about binary search? What makes it special as a searching algorithm?
It's sorted.
It's sorted. Well, the array needs to be sorted.
It splits the array in half.
It splits the array in half. Very good. So array needs to be sorted. Splits the array in half. Very good. Any other word for like splits the array? Like any other term we could use when we say splits the array?
Uses divide and conquer.
Divide and conquer. Very good. Very good.
Yeah. It checks the middle index. If it's not what it's looking for, it goes left or right.
Checks the middle index. Okay. Very good. What's about runtime? What's the runtime of it?
And log in.
Very good. Well, it's log n, right?
Maybe.
Merge sort would be n log n. But since it's splitting the array in half each time, it's just log n there. Because the array is sorted already. Right? Yes?
Yeah.
All right, very good. Awesome. So all what we just listed here is very similar. The components of that is very similar to a binary search tree, right? A binary search tree is a binary search tree because it has to be sorted, right? The tree itself has to be sorted. What does that mean? If I have a tree, anybody give me a number? I'm constructing a tree now. Give me a number of your choice.
12.
12. Okay, we start out with 12. How did she? Okay, 12. Somebody else give me a number.
5.
5. So now I'm going to put 5 to the left of 12, okay? This is the rules of a binary search tree. The rules of a binary search tree are such that when adding a value, the value if less than the roots value goes to the left, right? Otherwise, if the value is greater, if the value is greater or equal to the root value, where does it go?
Right.
Goes to the right. Very good. So here we have 12. This is the root. We have 5, which is the left node. 5 is also considered the leaf, a leaf because, why is it a leaf?
No children.
No children. So a leaf implies no children. Again, that's some review as well. No children. Okay. Give me a number greater than 12. Anybody?
32.
32, you said?
Yes.
Okay. So in that case, 32 is going to go to the right of 12. We'll have 32 here. All right. Somebody else give me a number. Any number?
48.
48, you said?
Yep.
Okay. So we look at 12. Is 48 greater than 12?
Yes.
Yes. We go to 32. Is 48 greater than 32?
Yes.
So we put 48 on the right of 32. Okay, so this here is a binary search tree. Why is it a binary search tree? It's sorted in order, right? Starting from the root, anything to the left of the root is smaller, guaranteed to be smaller than the root, right? Anything to the right of the root is greater or equal to the root, okay? So anytime you're inserting, you use that same rule to insert any node or any value that you want to insert into the tree. So the objective of today is two things. One, we want to write a function to insert into a binary search tree. And two, we want to be able to search for a value in a binary search tree. If we were to search for a value, say 24, right? How would we approach that? First, we look at the root. Is 24 equal to 12? We say no, correct? At that point, what do we do? Where do we go?
To the right,
Why do we go to the right?
because it's greater than 12.
Because it's greater than 12. Very good. So that's the biggest benefit of searching a binary search tree, right? Already, you are taking away half the tree by knowing the value. By knowing the value that you're searching for, you know if you're going left or right. With a regular tree, with a regular binary tree, right? We have like 12, we have 24, we have 5, we could have 10 here, right? We don't know if to go left or right when looking for a number, correct?
Right, because it's not sorted.
It's not sorted, right? So in that case, how do we search? How do we search for 5?
We'd have to go down the leaves until we found 5 in this one because we don't know if it's on the left or right.
Exactly. But how would you give me some sort of traversal method you'd use for it?
Mm-hmm.
So we're looking for one of the traversal methods.
Oh, middle out is the one, right?
What do you say?
Middle something?
Middle out. I like the name sounds really good.
Oh no, that's not from the show. Sorry. It's something, never mind.
Something order, right?
Yeah.
Anybody else wanna?
Is breadth traversal?
So we could do breadth first, traversal. Very good. Breadth
Depth first?
first. Depth first. Very good. So those are the two traversals we have, right? We have breadth and we have depth first, right? Very good. So depth first, basically, how many traversals do we have in depth first?
3.
3. You want to name the first one or any one of the 3?
In order.
In order. Somebody else?
Pre-order.
Pre-order. And the last one?
Post order.
Post order. Very good. Very, very good. So any of those traversals we could use to search for 5. But what happens now? What's going to be the runtime of that traversal? What's going to be the runtime? We said the runtime of our binary search is log n because we're splitting up the tree in 2. What is the runtime of our regular binary tree? Searching for a node.
Is it O of n?
It's O of n. Why is it O of n?
Because it's going through each one.
Exactly. Did everybody pick that up?
Is it's still O of n because if it finds, I mean I know track because you're saying it's right. I was just questioning.
You're saying like if we're looking for 12 and we get 12 right away, is it still O of n?
Right.
It's still O of n. Why? Because we say big O, we always look for the worst case scenario.
Okay.
Right?
Yeah.
Because worst case
I was thinking
is,
O of n because we might have to go after everything if we never find the value.
exactly.
We have to go through everything.
Exactly.
Okay.
So always
But
think
then
of
on the other hand, we might find it right away. So
Exactly. So always think of worst case. Very good. Because yes, we could get 12 right away, but worst case, we have to go through each node of the tree.
Right, because we might not even find it, and then we have to check everything. So
Very good. And this is a regular binary tree. So the big difference between a regular binary tree and our binary search tree, it's sorted. So the runtime of searching becomes log n, right? Because we know we go in either the left or the right of the tree. Everybody with me so far? Yes?
Yeah.
Yeah.
All right, very good. So this is a brief review and looking forward into what we're about to build. Great, so let us continue on. So using our tree example here, actually, let's just reconstruct it. We have 12, what number we had here? We had 12, 20, well, that's no. We had 12, 5, 32. 12, 5, and 32. Okay. We'll write the code out on our whiteboard, and then we'll go ahead and code it out when we're done. So first, we want to do insert. Right? I want to insert a node. Somebody give me a node that we want to insert. Just give me a number, a value.
16.
16. Okay. So we want to add 16 here. Let's go ahead and write the code for that. So 16 is going somewhere in our tree. We'll start out with a function. Right? So the function is to write the question is to write a function that takes in a value and inserts it in our binary search tree. So we start off with a function, we'll call it insert. It takes in some value, which is an integer. Doesn't return anything for now. Okay. Now, let's go ahead and continue. So first we want to see what's the value. So here we'll say if the value is less than, I'll say self here to denote self is going to be our tree node. Let me just put in a tree node here. We'll have a class, we could call it tree node. It has, what's the properties of a tree node?
Left and right children.
We have left, which is a tree node. We have right, which is also a tree node.
And value, right?
And we have value, very good. So value here. Actually, let's just call it, yeah, value, which is an integer. And we have our initializer, which takes in value of integer and self dot value equal to value. Okay, very good. For purposes of clarity, let's rename this to like new value. So here we'll say if new value if new value is less than value here. All right. So this value is coming from our tree node property, right? Everybody with me?
Yeah.
All right.
Yep.
So let's continue on. So here we're saying if new value is less than value, right? Where do we go?
The left.
The left. So go left. Okay. Great. So we're inside of our if statement now. Now we want to check if left, which is our property left, if left is not nil, meaning there's more nodes there, right? If left is not nil, well, what do we want to do? We actually want to recursively call ourselves, right? Why? Because we want to keep looking left. Everybody with me?
Yeah.
All right. So if left is not equal to nil, meaning if there's more values, like if there's a next value here, call it 4. If left is not nil, what do we want to do? We want to keep going left. So basically we want to call ourselves again. So insert, well, you want to call left dot insert, and we pass in new value. Okay, we pass in new value here. This is great. So now we just call in recursively the function until there's no more values in the left node. So now this is good, and we'll have an else statement here. So if the left, meaning if we had 5, if we're at 5 and 5 doesn't have any more left values, we just insert the value there. If the value happens to be 4, for example, right? So here in our else statement, we simply say left equal to tree node, which is our implementation of tree node here. And tree node takes in a value, which is new value. So this is the actual inserting logic, the inserting code for it. Okay? And that only applies if the new value is less than the current node's value. Everybody with me?
Yeah.
All right.
Yeah.
Stop me if there's anything that doesn't exactly add up here. Okay, great. So now this is only the left side. Now let's do the right side. The right side is very similar. We'll say else here. If, somebody walk me through it. If right.
If right value is greater than value, the new
First
value.
first we gotta check to see if left is not equal to nil, right? We did the value part already. So if, basically, if new value is less than value, we go left.
Oh.
Anything else, we go right.
Okay, all right.
So there's no like else if, like, right?
Yeah,
It's just an
yeah,
else statement.
it's just the else statement, yeah.
Very good. So if right is not equal to nil, then what we want to do, we want to call right.
Ourselves. Insert
Exactly.
right, that insert.
Exactly. So we want to call it recursively here. Insert, insert new value. That's that. And then in our else statement, that means there's no nodes, we just attach it, or we just attach it to the left value here. So left, not left, right. Right equal to tree node and, sorry, tree node, new value.
Yeah.
And we put an else here. We close this else, and we close our function. Great. So this is basically, we may have some typos somewhere, but this is basically the insert here. We look left. Well, we first evaluate if the new value is less than value. If it is, we go left. If left has more nodes, we keep calling insert again on the left value. If there's no more values and it is less than the value, we just attach it at the left, at the left child. Same thing for the right side. We look at right. Does right have more nodes? If so, keep calling recursively. If not, just attach it to the right node. Any questions about that? Hello?
No questions.
Okay, so let us go ahead and implement it in code, and then we will implement search as well. So just keep your notes handy, and let us go to playgrounds. So the playgrounds, you could just call your playgrounds binary search tree. Heads up, if I do get disconnected, we'll continue tomorrow. Not tomorrow, we'll continue Friday, because my computer is actually draining more battery than taking in. You know what? Did everybody take the notes down from the iPad? From the whiteboard?
Yeah.
Yeah.
Okay, I'm actually gonna detach the iPad right now. Okay?
Yeah.
Yes, we got the notes down?
Yep.
Yeah.
All right, hopefully that's gonna get more power in than power coming out. So let's create a new playground. New playground. Everything is going to be super slow. Probably should have just done the whiteboard for now. Let me also kill QuickTime. Okay, hopefully. So binary search tree. Okay, let's construct our tree node first. So class tree node. We have left, as we said, which is a tree node. Mark it as an optional because, again, maybe there's no left child. And we also have a right child tree node. And we have some sort of value, which is an int. And we need an initializer to initialize our int value. Int. And we have self value. What's our numbers? All right, so let's construct some nodes. We'll say root node is tree node. And value was 12. Okay, let's continue on. We'll write an extension on our tree node. Extension, tree node. And we'll write our function insert. Insert for our arguments or the parameter, we had new value is an int, doesn't return anything. And then we started out with our logic. So we said if new value is less than value, here we are going left. So go left, else we are going right. Then we check if left is not equal to nil, then we want to keep calling insert recursively. On left node. So here we'll simply say left insert new value. And else, that means there's no children to visit anymore. So we'll simply just attach the new value or attach the create a new node and attach as left child. So that's what we'll do here. We'll simply say left equal to tree node value. Okay. So that's for the left side. If the value is greater or equal to the root's value, so go left if new value is greater than root or current root. Current node. Cool. Other than that, we'll go left, we'll go right, sorry. So here we'll also check if right is not equal to nil. Then do the same thing here. Call insert recursively right child. So here we say right insert new value. If there's nothing else to visit, we simply attach a new node to the right. So tree node new value. And that's what we just wrote down on our whiteboards. So that's going to insert a new value into our tree node. Let me just put down it's some sort of tree node here. Actually, we'll do it down there. Can everybody see the function? Can I scroll down a little bit?
Yeah, we got it.
Okay, cool, cool. Very good. Let's just construct our tree, what it looks like. So we have 12. We have 12. We have 5. We have 32. This is what we have. Okay, cool. So we could actually test this by writing a next function to just print the nodes. So if this works correctly, our print statement should look something like this. Well, I want to print it in order. So it's going to be 5, 12, and 32, right? This is going to verify that our insert on our binary tree works, okay? So now let's go ahead and write a function, an in-order function. So function in-order traversal. And the reason why it's 5, 12, 32 also, and the reason why is because we have in-order traversal on our binary search, and then it's going to be printed ascending order, okay? So if it's printing ascending order, that verifies that our tree is a binary search tree. Everybody with me?
Yep.
Hello? I heard no?
Yeah.
Yes.
Okay. Okay, so we have our in-order traversal. Let's continue to write it out. So first we'll say left in-order traversal. We will print, just print out the value. So this is visit left, visit current node, and then lastly, visit right. So right in-order traversal here, visit right. And here we'll just simply print out what the value is. So print value. We'll just put like a terminator here. Terminator. Okay. Let's see what we have. So we have root node, which is 12. We could say root node insert new value, which is 5. And we could say root node, insert order value, which is 32. 32. And now we could test our print function, our in-order traversal print function. Argument, well, insert 32. Now just say root node dot in-order traversal, and let's see what we have. So here, again, we have 5, 12, 32, as expected. So that means we inserting correctly. Any questions?
Nope.
Alex, can you I can't see the end of the code.
Of the function?
Actually, no, just all the way down to what the last things. Just you just inserted and then you called an order on the root node. Okay.
Yeah, and we inserted, well, we have a tree node or the root node, and then we have 2 other values.
Okay, got it.
Mm-hmm. Okay, so next is going to be searching, right? So we want to be able to search for a value, for example. If I want to search for 5, how do I search for 5? Well, let's actually just write some notes here. So search logic. So now if I want to search for 5, what do I do? Well, I'll check the current node to see if that's the value I'm looking for. So first, check current node to verify target value. Second thing we want to do, so if 5 is not equal to 12, or 12 not equal to 5, what are we going to do at this point? What's the next step?
If it's less than the current node, we would go left.
Would go left, very good. So next step, if it's not, then if target value is less than current node value, then go left, or then search. Otherwise, else search. Well, otherwise, yes, search, else search, right. Right, because if target value is not less than, that means it's greater than or equal to. So then we're gonna go to the right side, right? So far, so good?
Yep.
Okay, so let's just copy this and then go implement search. Or cut and go implement search. We'll implement search right here. So function, we'll call it search. Or we could call it contains, probably better. If contains some value, we'll call it target value. Is an int. We'll just return a Boolean to indicate if it was found or not. Or if it was found or not, we'll just return some Boolean value. And very similar, we have step 1 here. Let's do that. So if target value equal to value, just return true. Okay. This here means it's equal to root on current node. Great. For step 2, let's go down to step 2. Step 2 says if target value is less than current value, then search left. So if target value is less than value, then we want to search left. Otherwise, we want to search right. Okay. Cool. So here, if we are in the left side of our search, then we want to say if left is not equal to nil, we want to call recursively, call contains recursively on left child. If we're in the else, that means we did not find it. We'll just return false here because there's no more nodes to search left here. So we return false. Let's actually just call this recursively. So here we'll say return left contains target value. So this handles the left side, and we'll go on to the right side. So if right child is not equal to nil, that means there's no more nodes to visit. So we'll visit them recursively. So I'll just visit recursively. And here we'll say return right contains target value. Else there's no more nodes in the right side to look at. We did not find our value. We just return false. Okay, so clean that up a little bit. So we have everything on one function. I mean on one screen here. Take this down a little bit. And we almost get the whole thing on one screen. Any questions about what we just did? It's basically the walkthrough we did with our tree node earlier before we implemented this function is the same thing. First, check to see if the value we are looking at, the current node's value, is the value we're searching for. If it is, our job is done. If not, if the value, the target value, is less than our node's current value, then we have to go left. If left has more children, we want to visit them recursively. If not, we haven't found a value. Else, we want to go right because this case here is false. So we'll go right, check to see right, is there more things to visit? If so, visit them recursively, else return false. And every time we visit recursively, we first check to see if the target value is equal to the current node's value, okay? So at some point, either we get to true here or we get to false, right, in our function. Questions? Questions?
No.
Okay, so let's go test it. Currently, our tree has 3 values. Let's search for some values. So root search contains 5. Does it contain 5? Well, we expect true. If not, we need to fix some of our code. Run that. We get true. Let's search for something that doesn't exist. Contains -5. Here we expect false. False. Great.
I got false for 5, I think.
You got false for this one?
Yeah.
Did you insert 5 here?
I inserted 5 and 32, yeah.
Did you get this print statement earlier? When you did this here, did you get 5, 12, and 32?
It's actually...
When you ran Inorder Traversal?
No, but I have a print statement in the function.
Okay, do you get 5, 12, and 32?
No, it's not printing out. Can I see the Inorder Traversal real quick? Left Inorder Traversal print value. Yeah, I have that verbatim.
It might be, let's see, your, what's the last, this function we just did, double check what's happening here. So we have target value. We check to see if it's equal to the value.
And if it is, you return true. If target value is less than value, if not equal to
So
nil.
this is one if block here.
Yes. Until the else statement, right?
Mm-hmm.
And the other else statement, if right, 1 minute. Yeah, I'm not sure why it's not working.
Your insert, double check your insert as well. So insert, based on the value we have, we check if it's less than our node value. If it is, we go left here.
Oh, that took up the whole thing. Hold on. I'm sorry, I'm missing a bracket somewhere. Left insert if. I think I fixed it.
Cool.
Yeah.
Awesome. Very good. Great. Any other questions or code errors? Cool. All right. So today we just took a look at binary search tree. It's very popular.
Can I
go
see
ahead.
the bottom of contains real quick?
The
when
bottom
you search
of
right?
contains.
Yeah, from search right. Just right there.
Yes, I was saying binary search trees are very important to know. They're very, again, efficient in searching. So today we took a look at constructing one, inserting into it, searching into it. We'll revisit this same playgrounds again to talk about deletion. Either this week or next week, we'll do deletion there. Deletion involves some more work to do as well. So we'll look at deletion next.